Now we're going to show you a code cracking tool in action. So first thing I'm going to do is I'm going to create a new secret message. So I'm going to go to Trinket, and I'm going to use my polyalphabetic cipher to create a new message. So here's my trinkets. And here's the polyalphabetic cipher with menu. I'm going to go ahead and run this. And I'm going to enter a new code word. So the code word I'm going to enter is just going to be 3 letters long. And I'm just going to use 3 letters this time because I want it to happen kind of quickly. And I don't want it to take forever. If you choose 4 letters or 5 letters, it does start to slow down a lot. I'm just trying to show you proof of concept. So I'm going to enter a code word. And my code word is going to be fowl, like falcons. Okay? Or maybe Kent. Ken, like Kent. All right. So my new code word is Ken. And now I'm going to create a message using my phrase Ken, which is 10, 4, 13. And so I'm going to encode a message. So here we go. I'm going to encode a message. What would you like to encode? I wonder if Snowy Snowflake is upset that we never go to the beach. Okay? So now it's going to encode this. And first it gets rid of all the spaces, and then it encoded the message. So here's my encoded message. Control C, so I've copied my encoded message. Now I'm going to go to another tool that I built called the cracking tool, which I will show you how to build in a second. And it's definitely a harder thing to build. Here it is. All right, so I'm going to go ahead and run this thing. And run. Oops. What? 271. Print. Then hours, print. I've got 1, 2, 3 here, 1, 2 there. Okay, sorry. All right, here we go. Oops. Go ahead and run this thing. All right, so the first thing it does is it tests a phrase, and this phrase got a score of -308, and this phrase, which is a sentence, got a score of 1,003. It built 17,576 possible combinations, each 3-letter combination. And now I'm going to try pasting the encoded message, which remember is the one that we just created with our 3-letter combination. And the letter combination we created it with was Ken, K-E-N. And let's see what happens. So first it goes through all of the different, it's literally checking all of these 17,000 combinations. And then it's trying to ascertain which one is most likely. And it counts up to 100%. And it will tell us which one is most likely at the end of its work. And I did it with 3 letters instead of 4 letters so that this whole demonstration would be faster. Okay, it took 27.9 seconds. The computer estimates that if we'd done it by hand with 1 code per minute, which is about right, I think, that it would take 292.9333 hours, so many days, 10 days about. And let's see what it thought was the most likely code, Ken. So it thought the most likely code was Ken, and I really didn't cheat. It really thinks the most likely code is Ken. So using this, we were able to break our secret code in 28 seconds. All right, pretty good. Now, let me show you how this program works. This program has a whole bunch of pieces. The first piece is it creates a function called decode score. Decode score takes a string, which is going to be in code, and then it's going to give it a score. It's going to say, how likely is this code to be English? So if you hand it this, it should give you a very low score. If you hand it this, it should give you a much higher score. So let's see how it does it. First thing it does is it crawls through the string, and it looks for the letter Q. And if it finds the letter Q in a string, and the letter is not followed by a U, it sends back a very negative score. I can actually get rid of this line here. It says score equals score minus 300. Really unlikely. Now it looks at some letters, and it says, okay, if the letter E is in the string, then I'm going to give it a positive 50 score, and if T is in the string, I'm going to give it a positive 36 score, and it actually counts how many times the E appears, how many times the T appears. E and T are the most common letters in English words, so it makes sense that you give those positive scores. But K is a very unlikely word to find in English words, or unlikely letter to find in English words, so I give it a negative 27 score. And the way I came up with these scores is trial and error, just testing different phrases and combinations and seeing if I was able to crack it, and this worked out pretty well for me. Next, I'm going to look for words, common words, and I went online and found the most common words in English. And these are the most commonly used words in English that are short. Now, the longer the word, like because, I should give it a higher number of points. I mean, think about it this way. If I had 10,000 random characters, how likely is it that the phrase B-E-C-A-U-S-E would show up in a list of random characters? Pretty unlikely. So I give it 300 points. Under, still unlikely, but more likely because it's shorter. And short words like is, I only give 50 points. Then finally, I return the score. Another thing I need to do is I need to build all of the potential combinations. And this builds all the potential combinations with 3 letters. And again, I only did it with 3 letters to save time. So it has an alphabet, and it has these nested for statements. If you look at them carefully and sort of think about this a little bit, you might realize why this works. But it will build all 3-letter combinations. This is a very simple function. All it does is if you hand it a phrase and it has anything other than these characters, it will take that character out. So all the punctuation, all the spaces, stuff like that, because we don't need that in our message. What this does is we use this with our Caesar cipher. Code takes one letter and shifts it. So if you give it a shift, it will give you a new letter. So it returns an encoded letter, and we used that before. Decode phrase actually uses an entire phrase and a code word. So in this case, it's going to use the code word can or whatever we try, and it's going to take a phrase and it's going to try to break down that phrase. So let's say you gave it our gobbledygook phrase and you tried it with a different code word like QQQ. This would be gobbledygook on the outside. So that's fine because we would then score it later. But that's what this does. It uses our code word, 3-letter code word, and our phrase, and then it tries to break it. This is the same code that we used in the polyalphabetic cipher program. Okay, now this function takes a list of all possible codes, then it goes through every possible code, and it decodes the encoded phrase using each possible code. Then it scores the result. It creates a final list of every possible code with a score attached. The return value is a list of lists, which looks like this. So here's the first item in the list: 0, AAA, 10, AAB, -14, AAC. This tells us that, that of these 3 possible codes, AAA, AAB, and AAC, AAB is more likely than AAA or AAC. This function is really simple, but it takes a long time to run because it's doing a ton of steps. So what it does is it says, okay, you give me a code list, and you give me the encoded phrase, so the phrase that is supposedly, or is in code. And then what I'll do is I will go through every single possibility and then add it to this list, this scored list. Except right here, it doesn't add every single possibility to scored list. To save time, it basically says if the score of scored list is not greater than 5 times the length of the encoded phrase, please don't do it. Now, you may say to yourself, well, why would we not do that? It's just to decrease the total list that we're looking at. This was arbitrary. I played around with different variables and different methods to get that list to be shorter. Okay, then finally I use a bubble sort to sort my final list. The only tricky thing about this bubble sort is right here, where it says I and then 0. Because I'm sorting a list of lists, I actually don't just sort the items. I actually need to sort the first item in each of the items. Okay, so that's what this does here, the I and the 0. And this just shows you that everything's working. So first it, First, it tests the decode score. So it prints out this thing and shows you what its score would be, and it prints out this thing and shows you what this score would be. So if we go to the top here, we can see that gobbledygook got a score of -308, but a sentence got a score of 1003. Then it builds the combinations, and it tells you how many combinations were created. It then gives you the first 10 combinations and the last 10 combinations, just to show you that it really did build them all. Finally, it asks you for the coded message. And then, let's see, what does it do? Oh, this is interesting. I could have said, please deal with all the combinations at once, but it's a really big list. It's 17,576 items. So instead, I wanted it to do 1% of the list at a time. So I created this thing called 1%, which I calculated up here. 1% equals 1% of the length, right, of the combinations. And then I basically go through it 1% at a time. That's what this does. And then last but not least, I print the top scores. So the top 50 scores are printed. I tell you how long it all took. And I then estimate how long it would take by looking at the length of combinations and dividing it by 60. So I do one combination a minute, so divided by 60 would be hours, and then I tell you how long it would take in hours. So it cracked the code in, as I said, 27 seconds instead of 292 hours. Hey, it's just an estimate. But you can see why the Germans thought that their code was so secure, and actually it really wasn't. Oh well. Actually, it's a good thing.